In a real communication system, not every frequency is useful. Some frequencies contain valuable information, while others may be noise, interference, or unwanted harmonics. How do engineers keep the frequencies they want and remove the ones they don't? The answer lies in one of the most important tools in RF engineering: filters. Every real-world signal exists in an environment filled with other signals. A receiver may pick up noise from electronic circuits, interference from nearby transmitters, or unwanted frequency components generated within the system itself. If these unwanted frequencies are not controlled, communication performance can degrade significantly. Imagine trying to listen to a single conversation in a crowded room. The information you want is mixed with many other sounds. Similarly, communication systems must separate desired signal components from unwanted frequency content. Without a mechanism for doing this, reliable communication would be extremely difficult. The challenge is creating a system that selectively allows certain frequencies to pass while suppressing others. This requirement leads directly to the concept of filtering. A filter is a system that modifies a signal according to frequency. Instead of treating all frequencies equally, a filter selectively passes some frequencies while attenuating or rejecting others. Filters are characterized by their frequency response, which describes how different frequencies are affected as they pass through the system. Frequencies within the passband are transmitted with little attenuation, while frequencies outside the passband are reduced. There are several common filter types. Low-pass filters allow low frequencies to pass. High-pass filters allow high frequencies to pass. Band-pass filters pass a specific frequency range, while band-stop filters reject a specific frequency range. Together, these filter types form the foundation of frequency-selective signal processing. Intuitively, a filter can be compared to a sieve used to separate particles of different sizes. The sieve allows certain particles to pass while blocking others. In a similar way, a signal filter separates frequencies rather than physical objects. Physically, consider an FM radio receiver. The antenna receives signals from many radio stations simultaneously. The receiver uses a bandpass filter to select the desired station while rejecting signals from neighboring frequencies. Without this filtering process, multiple stations would overlap and become unintelligible. Mathematically, filtering modifies the spectral content of a signal. Frequency components inside the passband remain largely unchanged, while components outside the passband are reduced. The output signal, therefore, contains only the frequencies that satisfy the filter's frequency response characteristics. Filtering is one of the most important operations in RF engineering. Transmitters use filters to remove unwanted harmonics and reduce out-of-band emissions. Receivers use filters to isolate desired channels and reject interference from nearby signals. In wireless communication systems, filters help manage limited spectrum resources. They ensure that signals occupy only their assigned bandwidth and prevent interference between adjacent channels. Regulatory requirements often specify filtering performance to maintain spectrum efficiency. At the system level, filters appear throughout communication networks, radar systems, satellite links, cellular infrastructure, Wi-Fi devices, and software-defined radios. Nearly every RF signal encounters multiple filtering stages before reaching its destination. Although filters are extremely powerful, no physical filter is perfect. Real filters cannot create infinitely sharp transitions between passbands and stop bands. Instead, frequencies near the cutoff region experience gradual attenuation, creating practical design trade-offs. A common mistake is assuming that filtering only removes unwanted signals. In reality, filters can also affect desired signals by introducing attenuation, phase shifts, or time domain distortion. Engineers must carefully balance selectivity against signal quality. The study of filtering naturally leads to signal distortion. Whenever a filter modifies frequency components differently, the shape of the original signal may change. Understanding this relationship is essential for designing communication systems that maintain signal integrity. In this lesson, we learned that filters selectively pass some frequencies while attenuating others, making them essential tools for controlling signal spectra. We also saw how filtering helps remove noise, reject interference, and manage bandwidth in communication systems. In the next lesson, we will explore signal distortion and discover how system limitations can alter the shape and quality of transmitted signals. If you found this useful, like the video, subscribe, and follow for the next lesson.